Thank you so much for the invitation. So thank you so much for the introduction as well. So I'm here to talk about EIC accelerator physics. Today is mostly terminology. I know some of you may have been in control rooms and had the misfortune of interacting with the accelerator physicists in the control room and hearing them mutter things about different terminology. So a lot of this is build up towards tomorrow, where John and I will both be talking about the EIC IR and detector from different sides. So in some sense, we started off our journeys on separate paths, and tomorrow we're going to tie it all together for you. So we were just talking about this graphic identity, by the way, which is for the EIC, and this picture of, there's so much detail in here in nuclear physics that's really interesting, including even complementary colors for mesonic quark pairs and C quarks and gluons and spins indicated and things like that. It's supremely rich if you want to spend 10 minutes playing with your friends, looking through all sorts of details that are built into that. Two things before I start, right? I teach a lot of courses on accelerator physics. All of those courses are on my website. So if you're really interested, want to dig into any of the background material, even videos of some of my courses, they're at your one-stop shopping place for accelerator physics. And if you have any input that you don't catch me between lectures, please, oh please, just use the email address. So let's give an outline for today's talk. At least I'm going to give a brief overview of the EIC itself. This is an EIC school, after all, from the perspective of an accelerator physicist, which I am. I'm going to go through a bunch of relevant accelerator physics terms because they are quite relevant to how I talk about the detector and the accelerator interface to the interaction region and the detector later on. Plus, they're just useful terms for you as experimenters to have and theorists as you interact with your accelerator colleagues as well. We'll get into luminosity later on, and then finally, I'll kind of get into the real driver for EIC. One of the main drivers is high luminosity. How do we produce that? I've got a little game you can play at the end that a friend wrote online, where you can actually work on maximizing the luminosity of a collider yourself and realize it's not as easy as one might think. So tomorrow, I'm pleased if you have anything you want me to address that's not on these lists, make a request, ask. I heard somebody asking about particle sources, whether polarized sources or heavy ion sources. I'm happy to talk at whatever length individually or within a lecture about them. But tomorrow there's going to be a lot of talk about why the luminosity curve for various energies of the EIC is the way it is, right? At low energies, we don't have as much luminosity. At high energies, we don't have as much luminosity. There are good reasons why. And walking out of my talk tomorrow, I hope you grow to understand that. A lot of that may look familiar to some of you if you were at the Gordon conference last September, October, I think it's last September, I think it was, up in New Hampshire. So I'll go through a lot of that background and throw a lot of accelerator physics luminosity limitations at you, and then close out with a projection and some understanding of why you don't immediately get peak luminosity out of a collider like EIC, as opposed to a fixed target machine like CBAF, which tends to produce peak luminosity almost from day one. So let's go into some of the requirements, right? I think all of you have internalized this and know this, but it's good to review them. And it's good to hear about them from the perspective of somebody who's got to build the thing, right? Certainly it's a high luminosity machine. This 10 to the 34th is a serious challenge. I will not mince words. This luminosity, and in fact, the integrated luminosities per data points of combinations of electrons and various ion species of 10 to 100 inverse femtobarons over years of running, those are quite high, right? Particularly, I'll make a point later on that higher energy accelerators, higher energy colliders make it easier to produce higher luminosities because beams are naturally smaller. Because of the energy range of this machine, this is an extremely ambitious number. Colliding highly polarized electrons and your protons and your light ion beams, right? These polarizations have been achieved for the most part with protons, for example, in RIC. But you have to also be able to flexibly include different orientations of spin to look at your systematics as you go through your experience. This is a world unique machine. There is no other polarized collider in the world, nor will there be for a long time. This large range of center of mass energies, I put low in here. Low energy, high luminosity, particularly challenging. But this is, this is low compared to something like LHC, compared to other, large colliders in the world. And there's a large range of ion species. I mean, we're going to get up to uranium, maybe even heavier ions in the long future. So it is a machine that has to jump through many hoops very flexibly, perform very highly or very well. And all of that makes for a really, really unique challenge in terms of the overall accelerator design. I know a lot of you are interested in the second IR. I will allude to some of it tomorrow. The second IR, I gotta say right now, it's preliminary design as part of the project plan. We have to ensure that this machine design supports the second interaction region. The actual final design is not part of the project right now. And, we'll talk more about the interaction region interfaces tomorrow. So what are the pieces, right? You need at least 2 accelerators to make a collider because you have to have beams and 2 separate accelerators. Those are very different accelerators for something like the EIC. Fortunately, EIC is being built on top of RIC. And I worked at Brookhaven from 1993 to 2010. I helped design, build, commission, operate RIC over those 17 years. I was the guy steering the beams when we saw first collisions at the star detector. So this machine, the RIC machine is very, very close and near and dear to my heart. Now we're going to tear out a bunch of it and put in some new accelerators for the EIC. However, we are going to reuse one of the hadron rings, this red line in there. So there's a hadron storage ring. That hadron storage ring already is surpassing RIC operations by a factor of 3 in terms of the overall beam current. That is non-trivial. You can imagine RIC has been around 20 years, and now we're going to push up that beam current by a factor of 3 above a very mature accelerator. To do that, we have to do a bunch of technical things like insert some sleeves to reduce something called electron cloud effects in that accelerator to keep the beam stable. So we have to manage that high beam current. That's the main challenge of the hadron storage ring. We also have to make the beams small. And I'll talk about emittance later on and define emittance, go into the background of some of it as well. But this 1.5 nanometer vertical beam emittance, I will belabor this a bit tomorrow in a slide or two. To get to that, we actually have to be able to literally cool the beams, reduce the hadron beam temperature. So the hadron storage ring has its own set of challenges in there. The hadrons go around counterclockwise in this collider. Clockwise in this collider go the electrons. That is the electron storage ring. 2.5 to 18 GeV, completely new for this facility. Its performance, 2.5 amps of beam current, is comparable to one of the best colliders in the world right now, a machine called CTEQ B in Japan, which is the world leading B factory, and in fact, the world leader in luminosity. That high beam current in this itty bitty living space, this machine is only 3.8 kilometers around. Remember, bending moving charges, accelerating moving charges produces synchrotron radiation. This machine produces a lot. 9 megawatts of synchrotron radiation is being thrown off of this electron storage ring as it's operating. And we have to continuously pump that energy back into those electrons. I'll comment more about that tomorrow as well. This beam current, by the way, people affiliated with Brookhaven may think Brookhaven just built an electron storage ring that's very modern and very new in NSLS2. There's this beam current is 6 times that. That design beam current of NSLS2 is only 400 milliamps as opposed to this 2.5 amps. Then we have to be able to inject those electrons. So we have to have a new injector that is also the full size of this facility for various reasons. And that injector has to be a full energy injector. So it has to go up to the same energy as this storage ring, because this storage ring does not accelerate the electrons, it only stores them. It has to cycle and produce new bunches for the electron storage ring and for the collider twice a second. Because as I'll show tomorrow, what happens is if you put polarized electrons into this electron storage ring, they lose their polarization over the course of minutes. And you have to replenish those electron bunches as they naturally depolarize because of beam dynamics. So this has to re-inject high polarization bunches to maintain a high 70+% average polarization of the electrons that you want for your experiments. And then there's the IR. We'll talk about the IR a lot more later on and tomorrow, including the future second IR. So these are the multiple machines in here. I'm not even mentioning the injector into this rapid cycling synchrotron. I'm not even mentioning the electron cooler, which is really its own separate talk in and of itself. This is a bit of an eye chart, as you can imagine, right? But this is one of the primary parameter tables that we use in the conceptual design report for the EIC. Later on, you will begin to understand some of this, but even though I point out a few of these lines, I do not expect you to understand them yet because I haven't explained what they are, including things like emittance. That's one of the points of this talk. So let's start with some background. Let's start with some terminology that you will have heard or may hear in the future, and also give some background into accelerator physics and how we design these types of accelerators. So first thing we do is we take, everything is electromagnetic. In my introductory lectures to 2-week accelerator physics courses or semester-long accelerator physics courses, I have an entire lecture on special relativity. I have an entire lecture on E&M, because let's face it, particle accelerators are the world-class demonstrations of special relativity at its most extreme and electrodynamics and interactions of charged particles with environments, either in detectors or in the accelerator physics itself of electrodynamics here. So this is Lorentz force, it rules. What we do first thing to make life easier, separate variables as much as we can. So these charged particle beams are ensembles of oscillators. We have to keep them, these things are going around this particle accelerator 80,000 times a second at nearly 4-kilometer racetrack for tens of hours. That is billions of revolutions around that particle accelerator. So they have to be very, very stable. We have to have restoring forces. And in fact, we treat every particle in that beam as its own little oscillator, whether a simple harmonic or in a more extreme case, nonlinear. So longitudinally, we have RF cavities that produce time-varying electric fields or restoring forces that manipulate the beams longitudinally. Accelerate the beams that are going too slow, decelerate the particles that are going too fast, keep the particles together in time as they travel around that accelerator at nearly the speed of light. So these devices typically operate, tens of kilovolts to megavolts. The frequencies of something like tens of megahertz to gigahertz. And these things are literally physically electromagnetic oscillators. They're designed to be very efficient, among the world's most efficient oscillators, particularly the superconducting cavities that have a natural, dissipation time, a Q it's called, of something like 10 to the 9th oscillations it takes for them to leak out 1/e of their energy. That is, that is pretty efficient. Because these are electromagnetic oscillators, you can immediately gauge their size, and I'll show you one tomorrow, from these frequencies, right? About how long is a gigahertz? If you're talking about something electromagnetic, well, 1.5 gigahertz happens to be 20 centimeters, right? Just speed of light. So that is roughly the scale of one of these devices at the gigahertz range. At tens of megahertz, they are much bigger, right? They are monsters, it turns out. I'll show you one tomorrow. One of our crab cavities is about nearly this big. And that's, that's big electromagnetic resonators. So these longitudinally focus and create bunches. Each one of these bunches, as you saw in that previous slide, if you were sharp-eyed, has about 10 to the 10th or 10 to the 11th particles in each bunch. A lot of the particles per bunch, a lot of bunches, about 1,000 bunches. That means, of course, a lot of particles moving around in high currents. So these things, because they're oscillators that resonate sinusoidally, the restoring forces they produce end up looking exactly like a pendulum. So this is not really a simple harmonic oscillator. It turns out in the small amplitude case, of course, it looks like that, but really we treat the longitudinal dynamics much more like pendulum dynamics. And pendulum dynamics with forced harmonic oscillators with different frequencies of drive going on as well. That's its own separate lecture and own separate area of research. But I'll concentrate on the magnet. So this was all longitudinal. Transversely is kind of more what you care about. Yeah, you care about the temporal resolution in your detectors, how short are the bunches when they collide. But you care much more about the divergence of the beams when they collide and how small the beams are when they collide, because that produces the luminosity. So I'll talk much more in this lecture about transverse manipulations, and that's all transverse magnetic fields. Just like John talked about magnetic fields in time projection chambers, gauging particle tracks. Well, that was solenoidal fields because you're looking at transverse motion. Here, we are guiding particles that are moving for the most part longitudinally, so we're producing transverse magnetic fields. Almost all of the magnetic fields that are used in accelerators are transverse to the beam direction, just because, V cross B is maximal when those two are orthogonal. Typically, you can have very, very weak magnets for very low energy beams, something like 10 Gauss, not so far from Earth's magnetic field, it turns out, up to monsters that are even above, many Tesla, to the point where the magnets have to be superconducting in the interaction region. We'll talk about that more tomorrow. This transverse focusing, just like longitudinal, you want to keep the particles confined in all of these dimensions. There are 2 transverse dimensions and 1 longitudinal dimension. That bunch is a 6-dimensional object living, 3 dimensions of position and 3 dimensions of velocity, moving around the dynamical system of this accelerator. Fortunately, for the most part, we use linear fields here. So because that linear restoring force for that focusing is there, it looks simple harmonic oscillator-like. First order, that's exactly what we get. So longitudinally pendula, transversely simple harmonic oscillators. What could be harder? Well, turns out a lot, because this is very much an approximation that all of these particles are independent and that all of these particles see their own unique fields. These particles all talk to each other electromagnetically within that bunch. These particles all interact with their environments electromagnetically. There's much more going on than just this, but it is a good first approximation. So, and then higher orders, you add messy nonlinearities, you get coupling between these degrees of freedom that's not treated here, and those environmental EM interactions are also complicated. So let's ignore the longitudinal and let's talk about these transverse dimensions. Like I said, at the end of this lecture, what I want to get to is why is luminosity the way it is? And to really talk about that, I need to talk about beam sizes, particularly transverse beam sizes. This is going to look a little familiar from John's lecture, although it's from a slightly different perspective. So since we're using magnets and talking about using magnets to bend beams transversely, you need to end up with some equations. This is a different derivation of an equation that you already saw in John's lecture when talking about TPCs. This momentum of a beam divided by the beam's charge now, because we have heavy ions in this machine that do not have Q equals 1, is equal to the magnetic field bending those particles times the radius of curvature of those beams. There is another equation that comes out of this argument, by the way, that has to do with the frequency at which particles go around. Turns out that this particular frequency, which is called the cyclotron frequency for particles moving in a circle in a constant magnetic field, won somebody a Nobel Prize. Ernest Lawrence built cyclotrons, essentially built on the realization that as you accelerated particles, you could actually have the magnetic field adjust with the energy and build the cyclotron to keep particles moving around and spiraling out in a way that kept this frequency constant as you accelerated them. So this equation, I repeat again, it's got its own name for us. It's called rigidity. And oftentimes you will hear accelerator physicists talk about the rigidity of the beam. Really is how hard is the beam to bend, right? One thing I love about writing this equation this way, well, first of all, there's a Q in there that John didn't include because he was talking about singly charged particles in the TPC, right? But these things are all beam properties. These things are all accelerator properties, right? The bend radius, you built the accelerator to have a design bend radius. Magnetic field, you built those magnets to have that magnetic field, constant magnetic field for bending, so-called dipoles as well. So this is a relationship that immediately connects the beam to the accelerator. And is one of the first things you have to use in the design, of course. And I am using truly through all of this, there are no non-relativistic approximations. As an accelerator physicist, I live in a relativistic world. P is beta gamma MC, right? Gamma MV. If you fold together the B and the C, the beta and the C. That beta is the relativistic beta. Later on, I apologize. I'm going to use a beta for a completely different thing, and you're going to have to know from context which beta I'm talking about. It is just, there aren't enough letters in the Greek alphabet. And it's an unfortunate fact of life that this is just the way it is. So this equation, even though we oftentimes talk about the beam rigidity, this part, even though the units are not obvious, we often talk about it in terms of Tesla meters, which is expressed in terms of the right side, just because it's then easy to calculate what strength magnet do I need to bend the beam by this amount. You have to be really careful when Q does not equal E, in particular for heavy ions, right? There's kind of a ZE in there. And John already showed this equation for momenta in GeV over C and Q over E. I encourage you, anytime you see an equation that you use a lot, try and write down a parameterized version like this in natural units, because it will be remarkable to you how often the coefficient ends up being of order 1. And that just seems to be the way that we naturally do physics. It's kind of an incredible and shocking thing to me. But it's a lot of the times it's true. Maybe 10 to the minus 1, maybe 10 to the plus 1, but this is of order 1, right? GeV scale beams are bent with meter radii by Tesla scale fields. Great. All natural units. So here's an application completely different than one that John pointed out earlier, the one that I stole from a lecture from Yoo-Jong Kim a little over a decade ago. And this is just, I want to do some momentum measurement of a particle beam coming in here until I pass it through a spectrometer. This is just like passing light through a prism. Different bending angles for different momenta. And now you can get momentum resolution bending through the spectrometer and separate out different particles with different momenta or different charge states if you're at FRIB or something like that. It is a useful exercise to go through this, right? To go through all of the math where you end up calculating out these different approximations here in the fully relativistic form, of course, because these particles, for the most part, are always relativistic. So I talked about bending. I talked about how particles get bent from constant magnetic fields, like in the spectrometer, of course. That's not the only thing we have. I had mentioned focusing. I had mentioned the need to focus our beams transversely as well. And we do that with quadrupoles. So dipoles change the angle of the particles, right? They bend the beams, change x prime, the angle of the particle relative to its intended design trajectory. Now quadrupoles, the next order, what you can do is you can expand out the magnetic field, a transverse magnetic field in the free space of the vacuum chamber that the electron or ion beam is going through, and expand it out in the Taylor series. To zeroth order, constant field at bends. To first order, first gradient of field, first derivative is constant, and that is a quadrupole field. You can build a magnet that does exactly that. 4 poles, north-south, north-south. And what you find is that, yes, because this was an expansion which contained no dipole field, the field in the center is 0, better be, because if there was field in the center, it would be dipole because of the expansion. So this is the first order term in a Taylor series expansion. You can imagine there are others, sextupoles, octupoles, decapoles, dodecapoles, dodecapoles. I don't know, sounds like a bird to me. But what these quadrupoles do, now you can see that our particle beam is moving in this direction. As I displace in one direction or another, let's say I displace horizontally and my velocity of a positively charged particle is into the board. So if I displace positively, got a positively charged particle bending into the board, oops, I'm getting a force, a magnetic force outward. So this configuration for a positively charged particle moving into the board is defocusing. It's pushing my particle away from the design trajectory. It's an anti-restoring force. If I flip everything, I can get a restoring force. And in fact, if I displace here vertically in the same conditions, displace vertically into the board, QV cross B, I get a restoring force. It's pushing down towards the center. Is that always true? Do I get defocusing in one direction and focusing in the other? Turns out Maxwell requires it. And that's kind of one discussion point. Sit down and do the little Taylor expansion and play with Maxwell. In a field-free region, you don't want any conductors in here, can't play any funny games. In a field-free vacuum, does Maxwell at this level of the Taylor series expansion require that you defocus in one plane and focus in the other? And the answer is yes. You cannot build a magnet that focuses in both directions. Why was that a slight little lie? Turns out that at very low energies, I pulled the wool over your eyes by talking about high energies. At very low energies, solenoids can focus. But that's at very low energies, like MeV for electrons, type of things. And a big collider like RIC, like EIC, forget about it. You are not going to get focusing in both planes with anything magnetic. So horizontal focusing is vertically focusing and vertical focusing is horizontally focusing. How am I going to build something with magnets that keeps all of my particles together in both these directions at the same time? Thankfully, classical optics comes to the rescue. And that is, you can build alternating optical systems between, this is one plane. Think of this as horizontal, where I'm focusing, defocusing, focusing, defocusing. And then in the vertical, this would be defocusing, focusing. It would look exactly the same, just shifted over by one magnet. And it turns out that in classical optics, you can build optical systems, write down simple matrices that prove that this system is still net focusing. This idea, I mentioned the cyclotron before, this idea almost won a Nobel Prize, right? This strong focusing idea was the origin, one of the machines that led the world in this strong focusing right here at Brookhaven. It's the alternating gradient synchrotron, alternating gradient of these focusing magnets. The other one, anyone? Bevatron? No, Bevatron was a cyclotron. Bevatron was not one of them. So there's the other one was the CERN PS. CERN PS was contemporaneous to the AGS, and both are the original strong focusing machines. So this idea that now you can carry beams from one place to the other and keep them confined transversely in both directions is a real game changer. Not only because you can do that, but because you can actually keep the magnets small. Something like the Cosmotron, those magnets were big, and the magnetic aperture had to be big because as the beams grew in energy, you also needed more aperture to contain them. That scaling doesn't apply to this idea. Sure, absolutely.
You said that, okay, so Maxwell's equations are not energy. But you said this thing about only being able to in two directions, focus in two directions, equal to the other two. That is an energy dependent statement. Is that what you said?
There's so this statement here for transverse magnetic fields is truly energy independent. The slight little lie about something like solenoids, and in fact RF cavities are the same thing, is because you can play a trick where you violate that assumption because you accelerate, you go into the solenoid and the solenoid focuses the beam, you accelerate the beam, and then you come out of the solenoid and the solenoid doesn't defocus the beam quite as much anymore because the beam is higher rigidity. So you can play tricks that way, but you have to accelerate the beam a substantial fraction of its original momentum because otherwise the disparity that you get, that net focusing that you get is in the noise. It's really, really small.
That's what it means to be lower energy.
Absolutely. That's right. Yep. So that's a good observant question. Thank you. So there are full lectures about, this optical system. You can go through the math, you can write down matrices, either classical optics matrices or accelerator physics matrices. Remember, vertical is the opposite of this, just shifted over one cell. But most accelerator lattices are designed in modular ways that include this type of layout of magnets. You look at almost any big accelerator in the world, EIC, RIC, LHC, PS, SPS, CTEQ, MSLS2, all of these machines have some lattice that looks repetitive and for the most part includes this design because it turns out you can demonstrate that this layout where you set the length corresponding to the focal length of these lenses, the right ratio, turns out to actually be optimal for the overall average beam size throughout the entire transport. You cannot make this beam pipe in here any smaller on average to get the beam from here to here all contained together. So photo is really, it's a workhorse of accelerator physics design. That's why it's one of the most common. So the strong quadrupoles, dominate the focusing. The reason why there's net focusing is you have a beam in here, and I'll show a movie in a second that really illuminates this. You have a beam in the focusing area, in the focusing lens that gets focused down. So the beam is naturally largest here in the focal lens, And then it gets focused down to a smaller area in the defocusing lens, which blows it back up again. So effectively, the focusing is stronger because the beam is larger, and the defocusing is a little bit weaker because the beam is smaller naturally within those lenses. That's kind of a hand-wavy word explanation, non-mathy explanation of why you get a net average focusing out of this sort of layout. But like I said, the horizontal beam size is largest in these focusing quadrupoles. And then the vertical beam size in the defocusing quadrupoles, the corresponding reverse of this, there will be a defocusing quadrupole there, and the vertical beam size will be the largest there. So let's actually let me move forward. Oh no, I'll go through some of this and then I'll get to the movie, because the movie explains some of this better. But I want to tie this in beforehand. So this layout here, this repetitiveness, periodic focusing, is also intrinsic in any accelerator that's a ring. Any accelerator that's a ring naturally has a periodicity of 1 revolution or 1 turn around the ring. So there are multiple levels of periodicity involved in the accelerator design. One of these little photo cells in here that are repeated many, many times around the accelerator, and also the periodicity of going around the accelerator, in this case, this way, once. So the hadron storage ring, the electron storage ring, and the rapid cycling synchrotron in the EIC are all what are known as synchrotrons. The word synchrotron explicitly means that you are synchronizing the bending magnetic field of keeping the particles in this constant radius circle, roughly a circle, along with the beam momentum as the beam accelerates. So you can actually hook up feedback systems that make sure that your momentum as you accelerate and your magnetic field end up rationing out to exactly the same constant here, and thus the radius is constant as you accelerate for a given charge state, of course. So synchrotrons are characterized by an average radius that's constant, but momentum that can change along with the overall bend field that changes. So remember, you separate out the RF and the magnets as well, and the circumference being constant, just like the radius being constant, right? So, but now this revolution frequency, as you go around, well, if the radius is constant and my velocity is pretty close to the speed of light because I'm highly relativistic, my revolution frequency only changes a little bit as I accelerate the particles. It does change. We have to accommodate that. They do change a little bit with the particle relativistic velocity, theta, V over C, or the particle momentum. But they are periodic focusing systems. Now you can take a periodic focusing system, either those photo cells, which are periodic on a very short scale, or the entire accelerator, which is periodic on a 1 revolution scale, and everything you want to have periodic boundary conditions because you want the particles to do the same thing every revolution around this particle accelerator. This type of approach, periodic focusing systems, has a long history, right? I mean, anyone that did quantum mechanics or solid state, looking at various solutions for periodic focusing systems, has seen all of this theory before, and it can be applied to particle accelerators just the same way. I mean, here is, a 2-dimensional periodic structure, some sort of an atomic lattice structure as well. Here, it's a little bit simpler. We've decoupled the transverse, so horizontal and vertical Dart mixing. So now you can write down a 1-dimensional simple harmonic oscillator with a periodic focusing force. This equation is known as Hill's equation. Probably seen it before, sometime in graduate school, maybe undergrad. And this is the homogeneous version because there is not a driving term, because all of the forces that are effectively acting on the particles from these quadrupoles are these restoring forces. And in fact, this is how you relate the gradient, the variation of field with amplitude in that quadrupole, which is constant, And there's that rigidity term to get all the units right in here. This is how you relate that to this particular Hills equation that has this periodic focusing. So the overall synchrotron is periodic, as are the repeated photocells. That's fine. That's really boring, right? Okay, I can make, look, I can make the particles go in a circle and keep them all in the accelerator and make them go in a circle. What's my luminosity? Well, I don't know. I mean, if I make a collider out of this, it's not going to be very good because I never particularly make the beams very small. What I want is I want to be able to break that symmetry and insert some additional section of magnets that breaks that symmetry and does something else, and yet still has the boundary conditions to match the periodicity of the overall system. That's what's called an insertion. And the insertion that I'll mainly be talking to you about is low beta, but to get there, I'm going to have to go through one other type of insertion before then. So you match the boundary conditions between these sections. Much of the accelerator is kind of boring. Gets the particles from there to there. Maybe with a few, additional hoops to jump through in between, because we want the beam to be big there for some measurement or small there for some diagnostic device or to get past some obstruction. But at the end of the day, the main insertion is getting the beam small for high luminosity. So now we finally get to just emittance, right? This Hills equation, second order homogeneous differential equation, it's an equation of motion. It's F equals ma in a different form, just like almost every other type of these dynamical systems. So since it's a second order differential equation, you have all of your motion is determined by initial conditions for an individual particle. So what you do is you talk about, just like in classical dynamics, its position and velocity, and then you let the system evolve, and the system evolves. Here you have position and velocity, or position and angle, as I launch my particle through my various magnets, and it evolves through the system. And that really is, instead of time, we use s, which is the distance along the accelerator, as our independent time-like coordinate, because it's much more natural for us, at least. So you can see now, because this velocity doesn't look like your traditional velocity, it's not got the right units. In fact, it's dimensionless. S is a distance, X is a distance. So X prime and Y prime are angles in radian, typically more like milliradians for an accelerator. And you have them separately for horizontal and vertical with these initial conditions. So here is a beam. The picture, snapshot of a beam from this movie I'm going to show you. And this particular picture is in a phase space, X and X prime for all of these individual particles at this particular moment in time. And that is quite often, that is not so far off from what a real beam looks like with about 10 to the 10th more particles than the 100 or so I've got scattered there. So this X and Y prime, you can already see here. These units here are order of millimeters. These units here are order of less than a milliradian. Milliradian is a pretty small angle. So a lot of the equations of motion that we write, a lot of the dynamics that we work through actually ends up using paraxial approximations. Particles have very small angles relative to their incredible forward momentum that they have going through the accelerator. Kind of no surprise, all of these particles are very high energy. So of course, the majority of the energy is going to be forward. I know that bothers you because it's very hard to put a forward detector in that intercepts the entire, very small angle deflection beam without seeing some of those particles that are slightly off momentum relative to the design trajectory of the beam, which is at 0, 0 here. But live with it. It's what you got to do. So this is also Gaussian-ish. May not look like it because the statistics are small. This ellipse is an ellipse intentionally drawn to capture one RMS of that Gaussian-like distribution. And the area of that ellipse in this phase space is what is known as the emittance. It's an area here in this particular phase space. Because it's an area, it's got the same units as the product of the axes, millimeters, milliradians. Tends to be on the order of, something like 1-ish. But we'll look at the parameter table again and see how big it is for the EIC. But when you hear accelerator physicists muttering about, oh, the emittance is this or that, or the emittance is blown, it's because this emittance, for some reason, because we didn't have the magnet set up right, got much larger than we expected it to be. Does this emittance change? Turns out no. Because of the dynamics, you can think of Liouville or something like that. This phase space area within the dynamics of the system is conserved. And therefore the emittance is relatively constant as you go through this accelerator millions and billions of times. So here's the movie, and now I got to spend some time on this movie because it is a movie that explains a lot of things and puts a lot of things I've been explaining together. So these are all individual particles, of course, moving through this accelerator. And time is this red line as the particles move through this accelerator here. Now, what you can see, first of all, is that the motion, for the most part, in the phase space is circular-like. Simple harmonic oscillators. It's not perfect simple harmonic oscillator. It's not a perfect circle. And in fact, it's kind of a little bit of a weird circle. It's more almost rectangular because particles, move over there and then move down and then slide over there and move up. And that is because of the multiple different elements within the system. What are these long sections doing? These are dipoles. You may as well treat them as field-free sections. In a field-free section, a particle with positive momentum will have a positive increasing position. No surprise, a particle that starts up there moves forward in position through one of these drift sections. And a particle that starts down here with a negative angle ends up losing position and moving in the negative direction. So through drifts, through these non-quadrupole areas, there is a shear in that phase space. Positive moves positive, and more positive moves more positive because I'm at a larger angle. I'm bucking it transversely. And same in the negative. But then what happens in the quadrupoles? Well, let's go back and play that movie again. So there is a drift. Moving forward, moving backwards. But then in the quadrupoles, what you get is you get something that goes up and down. It takes those distributions and it shifts them, not a shear in the horizontal, but now a shear in the angle. A positive particle here gets sheared down and a negative particle here gets sheared up, or a positive particle here gets sheared down and a positive particle here gets sheared up. That is because the restoring force is either anti-focusing or focusing, depending on whether you are positive or negative relative to that zero in each of those quadrupoles. So here, that's horizontally focusing. Boom, I took a particle that was running upward and I focused it back down. Going through another horizontal focusing, particle that has positive angle, changed it to a negative angle. I turned it in, I restored it. Right, same thing here, positive angle restored. And in the vertical, you see that there is a little bit, let's go back and look at the vertical in one of those. Right, so let's wait for this guy. In the vertical, what happens is I actually get some anti-focusing, but the vertical is so small there that it doesn't really matter that much. Right, the effect is much more profound in the horizontal focusing for the horizontal, and then the vertical focusing for the vertical. That's the net focusing that I was talking about. You can see the area of this ellipse, that emittance, is conserved as it should be for Liouvillean motion. You can see in this picture what's happening here. This is like if you're holding a screen in front of the beam, X and Y. The beam is getting narrow in one dimension and then narrow in the other. and alternating back and forth. But the beam is never getting particularly small. If I were to collide this with another beam, it would always be big in one dimension, and it would always give you a lousy luminosity. Various things can mess up that emittance. We'll go into some of them tomorrow. So now I want to talk one more thing. I mentioned, I apologized earlier about the beta function. This beam size, I can take a projection of this and get kind of a little Gaussian. And that little Gaussian gets fat and thin. The beam size in this Gaussian projection on position, or in here, even better, Gaussian projection in each direction is changing, right? The beam size is moving back and forth. The beam size is related to that emittance and what's called a beta function, an optics function that's being plotted here as you go through the accelerator. I apologize about the beta function, but it is the term that we use. And when you hear accelerator physicists in the control room, do not be surprised if it sounds like us going blah, 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 beta function, blah, 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 or blah, blah, beta star, blah, blah, because that's what it sounds like to us sometimes. So the beam size depends on this. This is another separation again, right? This beta function is defined by the magnets. It's defined by the optics and the focusing. This beam size and the emittance are both properties of the beam. So this is yet another one of those equations that connects the beam and the accelerator itself. Remember, the quadrupoles change position, steer the beam. Dipoles change the beam, change the angle of the beam. Quadrupoles themselves now focus the beam or change this beta function. And in fact, quadrupoles change the angle of this. So here's a picture of some of these beta functions pulled out from a paper just a couple of years ago about the high luminosity LHC and some different options for its interaction region design. You can see quadrupoles are set up on either side of that interaction point to try and produce either round beams at the interaction point or flat beams at the interaction point for various reasons. This beta function, which is related to the beam size again, is either, the same in both direct dimensions, and this beta star is that beta function at this interaction point, or it's rounded off for some reason, asymmetric between horizontal and vertical. But now you have enough experience, almost even just from that movie, to look at this picture and go, I barely even need this diagram up here. I know there's a quadrupole here because this beta function changes angle. There's a quadrupole right there. There's a big quadrupole right there. There's a big quadrupole right there. It's changing the beam focusing a lot, right? So these low beta quadrupoles or high beta quadrupoles, they're called. These are high beta quadrupoles near. They have to be strong to take those beams that are being diverged and focus them down to that very small spot for high luminosity in this particular interaction region. And then on the sides of all of this are extra magnets that then adjust these beta functions back to the periodic system, and match it back into a regular periodic lattice structure that you see in the arcs of the LHC. So these betas are the main beam size knobs. Whenever you hear us talking about betas, we're trying to make sure that these beam size knobs are right. And this beta star is the beta function that corresponds to the beam size at the interaction point. So now let's go back to the eye chart, right? Now you understand and have internalized some lines in here. That RMS emittance, horizontal and vertical, that is that emittance that has units of something like millimeter milliradians, except in here it's actually nanometers and we just forgot about the radians, right? But it has units of length. So in here, it's on the order of something like, 20, 30, give or take. And for the electrons, and for vertical, it's on the order of 1-ish. So these are not beams that have the same emittance, the same phase space area horizontally and vertically. This is that beta star, literally how much are we focusing the beams at the interaction point to produce the high luminosity that's listed down here, right? So let's take this set of parameters that feed down into 10 to the 34th luminosity, give or take. And you can literally take these and multiply them together and take a square root and figure out what the corresponding beam sizes are, because you just got that equation. And the corresponding beam sizes are in the order of tens to 100 microns or so. Pretty small beams. Typical beams in a regular accelerator lattice of this energy on the order of a few millimeters. So we are squeezing down the beams quite a lot to get this very high luminosity. And we'll talk more tomorrow about that, why that's a challenge. But now you can see, roughly what the scales are for all of these parameters, both the beta stars, how much we have to focus down the beams, and these emittances, how big these beams are intrinsically. And there are good reasons why we can't make those beams that much smaller. So I got a few more minutes and I got like 5 or 10 more slides, we'll see. So how do we make now an interaction region? Well, this picture here kind of already gave away some of it, right? There's a detector in here. That detector doesn't want any of these quadrupoles stuck in there because you don't want our quadrupoles in your detector and vice versa. So you have to be able to make a space, an area that is focusing free to be able to put the detector. So how does this beta function evolve through this region? It already is kind of illuminated here, but I drew another picture to just scale it out, right? So this is distance from the interaction point here, looking at a few different beta stars, going from 1 meter down to 0.1 meter down to 1 centimeter, which is not so far from what we're running in EIC. 1 meter is about what you run in REC, 0.01 meters or 1 centimeter is about what we want to run in EIC. And this equation, you can demonstrate, not homework, but it's certainly not too difficult to derive, is how that beta function now evolves with distance from the interaction point based on what that beta star is. It's a hyperbola, it turns out. And this vertical axis is square root. Be a little careful about that. This is like beam size. This is not like beta function. This is like beam size. You can see here, if you very, very strongly focus the beam, of course, it's going to blow up that much faster after the interaction point, right? And in fact, it blows up, something like the square root of the ratios of these beta functions. So it goes from something like 10 to 30 to 100, factors of 3, as I reduce my beta function by a factor of 10. But let's say, something to discuss, how big do you want to make your detector? Plus or minus 3 meters, plus or minus 5 meters? If you make your detector plus or minus 5 meters, your stay clear, my quadrupole out here now has to have a much larger aperture, a much larger size to accept that beam coming out than it would if you only made it plus or minus 3 meters. So I as an accelerator person, I want to put my quadrupoles as close to the interaction region as you can. You as a detector person want to give as much space for your detector as you can for the greatest acceptance. We have to come to some compromise somewhere for the luminosity that you eventually wanted, that we eventually want to deliver together. There is a limit to this. And that is, if we overfocus way too much, if we make this focusing way too aggressive, remember, the beam is not a point. The beam is a distribution of particles in all 6 dimensions, including length. So the beam is coming in, and okay, the front of the beam might be here, but the back of the beam might be up here. And as the beam goes through this, the beam itself might, as it passes through, literally develop an hourglass shape. And the average size of that beam, as it interacts with the other beam, is bigger than just the minimum. This is called the hourglass effect. And it is in fact something that limits our ability to make luminosity with a beam of a certain length. And in fact, we designed for it. If you go back to this picture here, hidden down here is a parameter called H, the hourglass factor. And we designed it so that for the bunch lengths that are available in the EIC, we end up throwing away about 10% of the luminosity of the machine. Now, if we wanted to make the focusing less strong, that's fine, but the luminosity would come down. If we wanted to try and make our bunches shorter, we can try, but these are already pretty aggressive parameters for our bunches. So this is the compromise that we ended up with, and one of the optimization points that goes into the longer talk tomorrow about the overall luminosity optimization of the EIC and why not all of these numbers are 10. There are good reasons why these numbers on the ends are small and these numbers in the middle are peaked. So I want to get to just a couple more things, right? Luminosity limits, you'll see this slide again tomorrow. You saw it at Gordon if you were at Gordon. I particularly want to focus though, on the minimum beam sizes at the IP, which I just talked about. This slide, it's really a useful exercise. These are the numbers we can get in RIC, right? About 90 megahertz collision rates, number of bunches, revolution frequency. These are the number of particles per bunch we can get, or total average currents. And these are roughly the beam sizes that we can get. You can take all of those numbers and just plug them into this naively, and you'll get about 10 to the 34. It really is kind of optimized in all of these different dimensions. But beam sizes at the IP is what I want to talk about, because I still haven't mentioned how we make the beams small in both dimensions. I mean, I alluded to that a little bit in this picture from the HLLHC, where there are a lot of quadrupoles in here kind of bouncing those beam sizes around until finally, somehow magically, both beams happen to be converging at the same time and go through minima exactly in the middle of the detector. So this goes back to that insertion concept I had talked about. The most trivial type of insertion, right? How do I make a smaller beam size and a longer magnet-free region that you can have a detector in? Well, one thing I can do is I can just space out some of my quadrupoles and make these lengths a bit longer. This is an example of what's called a pi/2 insertion. This is the periodic lattice. This is the periodic lattice. Everything is matched to them. But now I've drawn out some of these quadrupoles and set their lengths and strengths up in such a way that all of these boundary conditions match. And now you can see at least what I can do. I can't make, with just this many degrees of freedom, I can't make both beams small at the same time compared to the average in the regular photo lattice, but I can really gain in one of the dimensions, right? Or one of the other dimensions. And I can gain magnet-free length, right? There are quadrupoles at each one of these peaks. Remember, anytime you see a beta function turnover, there's a quadrupole there. But now, the only two quadrupoles are in here, and this entire space, which is longer than this space, this entire space is magnet-free, this entire space is magnet-free, this entire space is magnet-free. And you can start to see ways where, okay, I can play dumb games, like put lots of those things together, which is, already a little bit fun. But where I can start to design an interaction region that does that. And now you understand enough that you can look at a picture of Rick, a real machine that is really running literally now even. This is all photo. This is all that regular lattice stuff yet again. And this is from the design manual for Rick. Horizontal and vertical alternating focusing. But what happens at the ends is that it breaks that symmetry, and using just 5 or 6 quadrupoles on either side, it breaks that symmetry, has a long magnet-free region where those beams get big in both dimensions, and then turn over using 3 quadrupoles, triplet, and turn over and become small. at an interaction point in all dimensions and give you high luminosity. So you've learned enough to be able to look at this picture and kind of get a feeling for what's going on in terms of the design of the optics in RIC, which is kind of cool, right? So now this insertion, right, it kind of is from here to here, and then I make a mirror symmetric one over there, and I've got this minimum. And now the question is, how strong can I make these magnets, and how big can I make these magnets in terms of aperture to be able to push this down and maximize the luminosity? And that's the question that we'll answer tomorrow. It's really fun, right? This is, you can think of this as a transverse beam compressor or a transverse bunch compressor. So I'm taking an average size of the beam and I'm making the beam, literally as small as is possible in both transverse dimensions. There are analogs in longitudinal land as well, making bunches short. And you need to do that for things like free electron lasers and other types of accelerators. So now you know enough. We'll talk more about this tomorrow, of course, including the crab cavity, including the overall EIC interaction region design. Not sure if that's the latest picture, but we will talk about it, of course. And then this is the last slide, and this is something fun for you to play with. So I've got this equation, maximize the luminosity. Try and focus the beam in both transverse dimensions using only quadruples that can focus you in one dimension, and then the other dimension, and then the other dimension, and try and make this beam as small as you can. This is a fun little game from a guy named Stephen Brooks at Brookhaven, where if you load this web page from this site and then play with these quadruple numbers, you click on one of these, the beam will get smaller, and you click on the other one, the beam will kind of get defocused in one direction, focused in the other. But you can try and, if you let the beam get too big, oh no, it hit the beam pipe and we have beam loss. But if you make the beam small enough, up here is a readback of your live luminosity. And your job is to play this game and get to EIC 10 to the 34th, which is feasible, but hard. Just like the real EIC. The other thing that you can do is with this is you can even play funny games. You can turn on some of these higher order magnets, these nonlinear magnets. If you turn on a sextupole and start clicking on it, this thing becomes triangular, not round anymore. Or an octupole that becomes kind of, fourfold symmetric, squarish in some ways. These nonlinearities really do add up in an accelerator very, very quickly. So pull down the slides, play with this game tonight, see if you can get 10 to the 34th. And if you can, send me a screenshot so I can put it on the trophy rack or something like that. You may have to click on these. It says you can click on the arrow keys. For some reason that didn't work in my browser, maybe it'll work in yours. But if you just click on the little buttons here, it'll work. I can see somebody's already playing with it. So, and the smile that he gets. And that smile is because I'm done for the day. So it's time for lunch.